Hello everyone. Today's topic is Fresnel diffraction pattern due to straight edge. First of all, it's a Fresnel diffraction. We know that Fresnel diffraction we will have only slit and a screen. There will be no lenses. Okay, so that's why you are seeing here slit and screen. There are no lenses in between them. Okay, so and we are going to study about the Fresnel diffraction pattern due to straight edge. If there is an obstacle which is a straight edge, here you can see AB is the straight edge. This is a straight edge obstacle. Okay, and this is a slit. It's a narrow slit. It's not a point slit. It's a narrow slit. We know that for a point source you will get a spherical wavefront, right? If the point source is placed at infinity, you will get a planar wavefront. If there is a narrow slit or linear source, you will get a cylindrical wavefront. Okay. Since this point S is a narrow slit, okay, narrow slit which is illuminated by some source of monochromatic love. Okay, narrow slit. So the wavefronts will be like cylindrical wavefronts. Okay, something like cylindrical wavefronts you will get. So let's y is the cylindrical wavefront. Okay. Since this is a narrow slit, linear source, you will get a cylindrical wavefront. And AB is the straight edge, and this is the screen. Screen, we are considering a point P. Okay. The distance between the straight edge and the slit is A. Okay. And the distance between the straight edge and the point P on the screen is small b. Okay. So now what you will expect on the screen, since the light is exposed on the screen, what you will get above the point P, okay, the light will be exposed, so you will get a illuminated region. This region is called illuminated region. Above point P you will see some light, illuminated region. Do you see any light below P? Since there is an obstacle, it is expected that you will not see any light. Okay, that's why it is called below point P. This region is called dark region. This region and the dark region. Okay, you will not say. But in practice, what happens is above point P, you will see some diffraction pattern. Diffraction pattern means alternative bright and dark bands, like something you will see central maxima, secondary maxima. So there will be bright and dark spots above point P instead of a complete illumination. You will see up to certain distance, you will see diffraction pattern. That means it will have a maxima and minima. Okay, or bright band or dark band. Okay, you will see up to certain distance. After certain distance, you will see a complete illuminated region. There will be no diffraction pattern. You will only see a light. Okay, so it is observed in practice. So above point P, you will see some diffraction pattern. That means it will consist of maxima and minima bands. Okay, after certain distance, as you are moving from the point P, you will see complete illumination of the light. Whereas in below point P, it is expected that there should be no light because it is blocked by straight edge. So you should see a dark. But in practice, up to certain distance below point P, okay, you will see some light which is having intensity very less. Means as you are moving down, intensity falls very rapidly. So that means at particular distance you will see some light, but after certain distance you will see complete dark region. Okay, you will not see any light. Okay, so these 2 points are important. Above point P you will see a diffraction pattern, that means bright band and dark band. And after certain distance, as you are moving from the point P above P, you will see a illuminated region. And below point P, you will see for a particular distance, you will see small light with less intensity, and intensity will be rapidly decreases as you are moving, and complete darkness will come after certain distance. Okay, we will see why we are getting a diffraction pattern above point P and what is the intensity at point P. and what is the intensity at point P dash. Okay, and we will also discuss why the diffraction pattern is occurring above point P, and what is the position of the bright band and what is the position of the minima. All these things we will discuss in this class. Same here, I just written those points. Below point P is this geometrical shadow, above point P is the illuminated region. I just discussed, and I also discussed these points. Just above point P, you will see alternate dark and bright bands, that is diffraction pattern, and after certain distance, you will see complete illumination. Whereas in below point P, you should not see any light, but for a particular distance, you will see a light with less intensity, like intensity will keep on decreases after certain distance below P. Okay, so we will discuss explanation of the diffraction bands above point P. So above, I told you above point P, you will see a diffraction pattern, that means maxima and minima. So we will explain why we are getting diffraction bands. Okay. So since it is a Fresnel diffraction, Fresnel treatment is always like you will divide the wavefront into number of off period zones. Okay, that is the main concept done by used by Fresnel. Fresnel, what he did, he always divide the wavefront into the number of half period zones. You see here, from A to M1 is the first half period zone. So AM1 is the first half period zone. Similarly, M1, M2 is the second half period zone. M2, M3 is the third half period zone. Similarly, M3, M4, M4, M5, there will be n half period zones. So see, divided wavefront into number of half period zones. We know that the distance from the point to M1 will be B plus lambda by 2. Why lambda by 2? So we know that each zone differ by a path difference lambda by 2. That's why B is the path plus there will be a path difference lambda by 2. From first to second, B plus 2 lambda by 2. Second to third of period zone, B plus 3 lambda by 2. So on. For the nth of period zone, B plus n lambda by 2. Okay. Uh, mm, excuse me. Okay. Uh, mm, okay. Then coming to this point, since we are now explaining the diffraction bands above the point P. So as I told you, from point P1 to M1, which is B plus lambda by 2. Similarly, P to M2, B plus 2 lambda by 2. Up to n of period zones, it will be B plus n lambda by 2. Okay. Now, what we want to do is we have to find the intensity at point P. So to find the intensity, first we have to find the amplitude. Okay. So to find out the amplitude, uh, what I am considering is to know the intensity at this point, we have to see how much light is getting exposed at this point P. So if you see from XY wavefront, only the upper portion from A to X, from A to X. So I will just use the pointer. So this region A to X is getting exposed at this point P, and A to Y portion is blocked by this obstacle. Okay, so there will be no light from the A to Y. So only you will get A to X wavefront light at this point. Okay, so if you see, there are two regions here. This is one region, and these are the off period zones. Okay. So this wavefront is completely divided into the number of off period zones, like n off period zones. So to find out the amplitude, last class in Fresnel's off period zone, I told you that at any point P, if you want to find the amplitude due to the Fresnel's off period zone, we have to consider odd off period zones as the positive amplitude and even off period zones as the negative amplitude. Okay, so amplitude will be it will be like this one. So amplitude is equal to A1 is the amplitude of the light coming from the first off period zone. So since I told you odd off period zones are positive and even off period zones are negative. So that's why I'm taking is A1 as the positive and A2 is the amplitude of the light coming from the second off period. That's why it's a minus A2 and plus A3 since it is odd off period zone, again plus. So you can go through once Fresnel's off period zone where we have derived the amplitude. So same formula we are using here. So A1 minus A2 plus A3 minus A4 up to AN. If AN is the odd number, you will get a plus AN. Okay. So same expression I am just rewriting into the different format, like A1 is splitted into the two terms, A1 by 2 plus A1 by 2. Okay, A1 you keep it like that, all even numbers you just keep it like that, and just odd terms will be splitted into the two terms, like A1 is splitted into A1 by 2 plus A1 by 2, A3 is splitted into the A3 by 2 plus A3 by 2. So just rearrange them. It looks like a arithmetic progression terms, A1 greater than A2 greater than A3. So if there are three terms, A1, A2, A3, in arithmetic progression, if you want to find the middle term, it will be the mean of the other two terms. Like suppose if A1, A2, A3 are there, if I want to find the A2, A2 value is arithmetic mean of the A1 plus A3 by 2. Okay. Similarly, A3, A4, A5 is there. If you want to find the A4, A3 plus A5 by 2. Okay. So if you substitute these terms, we will get these terms as 0. Okay. This term will be 0 since A2 equal to A1 plus A3 by 2 minus, so this term will be get cancelled. Okay, similarly this term will be get cancelled, so only you will left with A as A1 by 2. Okay, so A as amplitude at point P as A1 by 2. So if you know the amplitude, intensity is nothing but square of the amplitude. Okay, so I is equal to A1 square by 4. So this is the time you got. So at point P, due to the Fresnel's off period zones, the complete intensity at point P is A1 square by 4. Okay. Now I want to find what is the intensity at point P dash. Till now we have found intensity at point P dash, at point P. Sorry. At point P, just now we got the intensity, which is nothing but A1 square by 4, right? Due to this complete wavefront A to AX, our amplitude is nothing but A1 by 2. Okay, at point P only. Now I want to find what is the intensity at point P dash. Okay, so this point I want to find what is the intensity due to this complete wavefront AX. So to find out the intensity, what I am doing, I just making a draw a line connecting to the slit to point P. For point P dash, C will be the pole. Okay, it's a pole. Okay, for point P dash, C will be the new pole. Okay, now I want to find the intensity at point P dash. So at point P dash, you have to see which light is coming. See, from point P there are two portions. This is one portion of the light, this is another portion of light. I will draw once again here. Okay. So at point P, if you see, complete AX is getting exposed, but this time AX portion is divided into the two portions. This is one portion which is a complete wavefront. Let's say CX is the complete wavefront. Okay, wavefront, whereas AC portion is Fresnel's, what he did is he divided into the number of half period zones. For time being, he initially divided, let's say there is only one Fresnel half period zone. Between the A to C, there is only one half period zone. Then what will be the intensity at point P dash? So first we have to find the amplitude. So amplitude will be at point P dash will be, due to this complete wavefront, we have just now derived amplitude is something like A1 by 2. So ikkada point P daggara, due to complete wavefront, we have derived the amplitude as A1 by 2. So due to this complete wavefront also, at point P dash you will get a A1 by 2 amplitude, and as well as, since there is only one half period zone in between this A to C, you will get the amplitude of the first half period zone. Amplitude of the first half period zone is nothing but A1. So complete amplitude will be 3A1 by 2. Okay. So due to one off period zone, initially I am assuming there is only one off period zone in this region. Okay. Because of this off period zone, the amplitude at point P will be A1. Because of this rest of the wavefront, amplitude will be A1 by 2. So total amplitude will be 3A1 by 2. Okay. Intensity will be square of this amplitude. Okay. That is called 9 by 4 A square, A1 square. So this is the maximum intensity at point P dash. Whatever the bright band you are getting, it is called first maximum. Okay. So if you say notes, I have just done same thing here. At point P dash, I am finding the intensity. For that, what I am considering is there. Here I will draw once again so that you will clearly understand. So there is a straight edge obstacle. Okay. There is a screen, and this point is P. Okay. This point is P, and there is point source S. Okay. So there is a cylindrical wavefront. Okay. So this point is called A. Okay. If you, I want to find the intensity at P dash, so I'm just connect from S to P dash. Okay, at P1. So this point is the new pole C. Let's say point is the C. This is the C. So because of this wavefront, okay, that is called CX portion. Okay, this CX portion, ఈ portion వల్ల ఈ పాయింట్ దగ్గర amplitude ఎంత ఉంటుంది అంటే A1 by 2. Okay, because of the CX portion, you will get amplitude at point P dash is A1 by 2 plus. So there is, we are assuming initially there is only one off period zone. So off period zone, first off period zone నుంచి వచ్చే amplitude అంతా A1. Okay, so you will get finally 3A1 by 2. So this is the amplitude term we got it. Okay, so intensity will be square of the amplitude, so it will be 9A square by 4. That is called first maxima. Now suppose in the same portion, once again I am drawing here. Initially this is straight edge. Okay, and this is screen, and this is source point P, and this is point P dash. Okay, so this is a cylindrical wavefront C. Let's say A X. Okay, you join the source and P dash. This point is C. Okay, now earlier we just considered there is only one off period zone. This time let's consider there are two off period zones are there. Here there is, sorry, there is one off period zone, and there is another off period zones, or two off period zones in this portion A to C low. There are two off period zones, whereas this CX is the rest of the wavefront. So at this point, what will be the amplitude? Because of this CX wavefront, you will get just amplitude A1 by 2. Okay, this is common everywhere. Plus, since there are two wavefronts, because of the first off period zone you will get a1. Okay, second off period zone, the amplitude at point p you will get is a2. Okay, but I told you odd numbers will be positive and even numbers will be negative, so minus a2. Okay, so this will be 3a1 by 2 minus a2. Okay, so intensity will be square of this amplitude. Okay, so that is what here I am writing. Okay, so intensity as compared to the first value, this will be less value. Okay, because you are subtracting the a2 from 3a1 by 2, so it will be less value as compared to the i1, so we call it as minima. So first minimum. So at this point p dash, you are getting first maxima intensity value this one, second first minima intensity value this one. Similarly, if there are three off period zones, what happens? So you have to just add the 3a1 by 2 minus a2 plus third off period zone. Odd means positive. Okay, so this is the second maxima intensity. Similarly, if you want from, if there are four off period zones in this region, so it will be added as minus a4, so on. If you want to find the an, just up to an you have to write these terms. Okay, so here intensity at point above P will be maximum if the number of off period zones in CA is odd. If there are odd terms, always the intensity will be maximum, because odd terms will give you the positive value. Okay, you see this odd term positive, odd term positive. If A plus A5, all odd terms will give you positive. If there are odd terms, you will get a intensity maximum. If you want to get the minimum, there must be a more even numbers. If there are more even numbers, you will get a minus term. So that's why intensity will be minimum when even off period zones are there. Okay, now we have found the intensity at p and p dash. Okay, and also we have found intensity of the first minima, first maxima, second minima, second maxima. Now I want to find how far the maxima occurs from the point p. How far means, let's from center P. So this is the point P. From this point, okay, from this point, how far there will be a first maxima occurs. Diffraction pattern is something like this, central maxima and the first secondary maxima, second secondary maxima, third maxima on right side. Okay, similarly, first secondary maxima, second secondary maxima, third one. I want to find how far from the center where we where you will get the first secondary maxima, second secondary maxima, and that means distance from the p for the first secondary maxima or second secondary maxima. How can I no? I want to find the position of the maxima and minima. So to obtain the maxima at point p dash, we know the condition that in diffraction pattern the path difference is equal to 2n plus 1 lambda by 2. Then you will get a maxima condition. Okay, so in diffraction pattern, always you remember, if the path reference equal to 2n plus 1 lambda by 2, you will get a maxima. You will get a maxima when the path difference equal to 2n plus 1 lambda. If you want to get the minima, path difference must be equal to n lambda. Okay, you just remember those 2 points. If the path difference equal to n lambda, you will get minima. That also I will discuss later. Okay. So for time being, if let's suppose we are getting some maxima here. Okay, we know that the path difference equal to 2n plus 1 lambda by 2, then only we will get maxima. Okay, so I want to find the path difference between the ap dash and cp dash, since the two lights are coming from this source. Okay, so this is one path, one path. this is another path. So path difference will be AP dash minus CP. Okay, so this is what I am writing. So that path difference equal to n plus 1 lambda by 2. To find out the AP value, AP dash value and CP dash value, okay, what I will do is I will assume the right angle triangle APP dash. Okay, this is a right angle triangle. Using the Pythagoras theorem, one can find the AP dash. Okay, hypotenuse square. So AP dash will be square root of b square plus x square. Okay, now I want to find the CP dash. How can I find CP dash? In this right angle triangle SPP dash, okay, CP is just a portion. So if you know the SP dash, if you know the SP dash, we can find the CP dash, because SC dash is approximately equal to SCA. Okay, so SC is approximately SCA. So we know the SC value, which is A. Okay, if you know the complete distance, we can find easily CP dash. To find the CP dash, what I am just assuming this right angle triangle SPP dash. Okay, SP dash will be something like this, square root of a square, square root of a plus b whole square plus x square. Okay, so we got the SP dash. So to find the CP dash, okay, SP minus a, which is nothing but this equation. Okay, square root of a plus b whole square plus x square minus a. So we got CP dash and AP dash. So using those values, if you substitute in the first equation, AP dash minus CP dash is equal to 2n plus AP dash value, substitute, this is the value AP dash. CP value is nothing but this value. Okay, so by substituting this one, you will get 2n plus 1 lambda by 2. Okay, so just rearrange these terms. You will get so here b is taken outside. Okay, so if you taken outside, it will be 1 plus x square by b square whole power of, okay, minus again a plus b taken outside, so it will be 1 plus x square by a plus b whole square whole power of, and this minus is minus plus a, will get like this. Okay, so b into 1 plus x square by, again this is the binomial expansion, 1 plus x whole power n is equal to 1 plus n x. So ikkada 1 plus x square by b square whole power of ni directly I am writing using this equation. I am writing like this one. Okay, so 1 plus x square by b square whole power of term will become, using this formula, 1 plus x square by half will come here, so 2b square. Okay, so this is the term I am writing. Again here half will come here, so you will get 1 plus x square by 2 into a plus b whole square plus a is equal to 2n plus 1 lambda. So if you cancel out the equal terms, you will finally end up with this equation. Okay, x square by 2 into 1 plus 1 by b minus 1 by a plus. So finally you will get the expression as x square by a 2b into a plus b is equal to 2n plus 1 lambda by 2. Here x is the distance from the point p where you are getting the maxima. So to find the x value, what you will do, to find the x value will, so to find the x value, so you just take these terms to the other side, so finally we'll get x as this term. So here if you see, x maxima means position of the, so ఇక్కడ diffraction pattern ఇలా ఉంటుందమ్మా. Okay, so first secondary maxima, this is called maxima. Okay, so first maxima, second maxima. Okay, first maxima position x max is directly proportional to the, in this equation చూస్తే root 2n plus 1. Okay, so n is, let's suppose 0, it will be square root of 1. Okay, so first secondary maxima is approximately proportional to the 1 into b plus a b into a plus b by a into lambda. Okay, so if you want to find the position of the maxima, you have to use this position formula. Okay, if I ask you to find the what is the position of the third maxima, what you will do, you keep the n value as 3, so that you will get the position of the third secondary maxima from the center. Okay, similarly you can do for n values. If I want to find the minima, as I told you, path difference must be equal to the n lambda in diffraction pattern lo path difference n lambda ki equal aithe we will get the minima. So ikkada path difference value we have just now derived, x square by a by 2b into a plus b is the path difference between the two lines coming from the slit. Okay, so this is the path difference formula, x square by a by we just now just now derived. This is the path difference. We are just using this formula here directly. X square by a by 2b into a plus b is the path difference between the two light rays coming at p dash. If it is equal to n lambda, you will get a minima. Minima means this point. So this point is called minima. This point is called minima. So ఇక్కడ first secondary maxima, second secondary maxima కదా, ఈ points we call minima. Okay, to find the minima position, if you equate this path difference equal to n lambda, you will get the minimum position from the point p. ఎంత దూరంలో ఉంది డార్క్ పాయింట్ అన్నది మనకి ఈ ఫార్ములా ద్వారా తెలుసు. సో if you want to get the x value, just take these values other side, so you will get x as proportional to the root n. Okay, so this is a complete picture about the Fresnel's diffraction pattern due to the straight edge. Okay, if you go to the previous diagram here, so there is a narrow slit here and there is a screen. Because of this straight edge, what kind of pattern you are getting is, we have just now discussed at point p how much intensity, at point p dash how much intensity is there, and also diffraction pattern law, bright band what is the maximum position, and also what is the minimum position also we have just now discussed. So if below point p, intensity will from point to p below there will be no light actually, but for a short distance there will be some light with less intensity. Okay, so intensity will be also it will drops off very rapidly. Okay, so that's why this diagram shows at the last point. Okay, I'll draw this one. So this is at point p. Okay, above point p you will see some bright band and dark band. Okay, so this is called bright points, bright bands, and these minima points is called dark points. Okay, after a certain distance you will see complete illumination of the light is completely illuminated. But below point p, as I told you, for a particular distance the intensity falls very rapidly. So this is a diffraction pattern in the Fresnel's off period Fresnel's diffraction and due to the straight edge. Okay, so please go through the notes, Fresnel's off period zones and zone plate and diffraction due to the straight edge. Okay, if you have any doubts, please post me or comment me on YouTube channel or WhatsApp also, you can ask me. Okay, anytime I will be available, just ask me anytime. I will try to clear your doubts. Okay, thank you very much. I will start polarization topic in couple of days. Thank you.